In this video, I'm gonna introduce you disjoint sparse table, which is an optimization of traditional sparse table. This gives us a better time complexity in problems solved using a sparse table with big nodes. Let me tell you the problem description again. So our problem is the same. Given an array and queries of type L and R, each query asks for the minimum in the range from L to R. This is the RMQ problem, range minimum query. We tried to solve it using different methods in the previous videos, and now we are gonna solve it with something new. But before that, let's see what happens in this example. So in this example, a query comes from index 3 2, 4, 5, 6, 7. So we want to find the minimum of elements in this range, look, like from here to here. So we have 2, 6, 2, 5, 7, and minimum of them is 2. So what we want to start in today's video is divide and conquer. So if we forget about all the sparse table and square root techniques we talked about and Arpa trick and so on, let's forget about them. And also, if you know segment tree, forget about that too. We have a very easy divide and conquer algorithm to solve RMQ. How it works. So we divide the array into two parts. And now we answer queries that contain the middle of the array. So as you can see, like the query mentioned here, this query, it starts from here to here. So it contains the middle point of the array, right? So I can say minimum of this is actually minimum of this range and minimum of this range. So what we make is an prefix mean array and suffix mean array. What are they? So prefix mean, it starts from the first element in the right part, this one, 5, and then processes elements one by one, and it keeps the current minimum. So it's at the first 5 and then 5 because 7 is not smaller than 5, and then 0, and it remains 0. And here it's 2, then 2, then 2, and it changes to 1 and remains 1 for the rest. So when I want minimum of a range like this, I can find minimum of this range, which is this one, and minimum of this range, which is this one. And easily, I can find the minimum of this range with asking just two elements in the prefix mean and suffix mean, and that's it. So you can see divide and conquer can easily answer queries that start in the left part and finish in the right part. So what happens if the query is completely in the left or right part? For an example, consider a case. It only consists of some range in the left part, like here. It's this range. So for answering this range, we can't use the middle line, right? Then we break the array into two parts and go solve these range separately. Like here, we want to answer queries for this. We write some middle line here, and then we answer, we make some prefix mean, suffix mean, and then we can find the minimum. That's very easy. So what is the benefit of using this approach instead of normal sparse table? So in the problem we discussed right now, actually there is no benefits, because the sparse table actually solved this problem with O n log preprocess and then O1 per query. That's right. But consider some problems that you have some special node, like, do you remember GSS1 we solved? So in that problem, we had some struct at each node of a sparse table, and we were using it and merging was a bit costly. But now consider the case that it's more costly. Like you have a very big node, and when you want to merge it, it will become very costly. So first of all, in some problems like GSS1, if you remember, we were unable to answer queries in O1. Why? Because we couldn't use two overlapping rings and merge them. We had to consider all log n segments, finding answer for each of them, and then merging them together. So this trick solves the GSS1 with a better time complexity. Actually, it answers every query in O1 instead of O log. And also, if merge operation gets more complicated, like it's for example OK, then using this technique like divide and conquer, it will lead to just OK for merging, that's it. But if you use a sparse table, you need to pay cost of K squared. We'll discuss it later. But what is the so-called disjoint sparse table? Disjoint sparse table actually keeps all of these prefix and suffix arrays calculated in divide and conquer to answer the queries afterward. So pay attention here. There are two different algorithms, but they are very similar. So divide and conquer and disjoint sparse table. In divide and conquer, we answer queries offline, but in disjoint sparse table, we keep all of the values calculated in the divide and conquer and answer the queries afterward, and for sure, we answer queries online. So if we want to compare these two, divide and conquer has easier implementation and it's easier to understand, and also it has better memory. Why? Because disjoint sparse table wants to keep all of these values, right? All of these values, they cost n log, but divide and conquer costs only on. So, but disjoint sparse table has some features, like it's O1 per query. It can answer very efficiently, but if you implement divide and conquer very naively, it will lead to you need to move queries from the root, from the beginning, from the whole array to the smaller ones that it costs actually log, but you can find a way to directly push the query to the node it belongs to. But in disjoint sparse table, it's O1 per query, and also it's online. Personally, I ultimately prefer divide and conquer. Why? Because it's easier to implement, easier to understand, and almost always we are not forced to answer queries online. Take care that also that the disjoint sparse table can handle queries online. It can't change any element. So it's not like segment tree, if you know segment tree. It can't change elements. It can only answer queries online. But I've seen only a very few amount of problems that force you to answer online. So in my opinion, disjoint sparse table has very few use cases, and actually it comes from divide and conquer directly. So it's like you use divide and conquer, you save all of the values, and you answer queries. It's almost the same. So now we are gonna solve a problem on this. So this problem is from USACO. Problem says we have an array A. So the problem, the array consists of some elements. Elements are not that big actually. They are at most 20. So they are in the range 1 to k, and you are given some queries. Some queries of form L and R, as we see before. And it asks you to compute the number of non-decreasing subsequences in the subarray modulo 10 to the power of 9 plus 7. So take a break here, think for at least 15 minutes, and resume the video. Now that you are back from the break, don't forget to like the video and subscribe to not miss our future videos. Let's describe the solution for this problem. So our problem was this USACO problem. So you can come up with 3 different solutions. First is using very normal sparse table. So let me define the DP we need to use in this problem. So we need a matrix. In cell ij, ith row and j's column, what we write is how many subsequences are there starting from I ending with j. So it's somehow related to LIS problem. So we start from I and we end at j. So in each node of a sparse table, what we keep is number of non-decreasing subsequences. Starting with I is the value, not index. Ending with j. So when I want to calculate a node in a sparse table, I have 2 nodes that they consist this big node. How I'm gonna merge these 2? For merging them, I need to do a for loop on the middle element here in between, and then it's like ijk, and I update ik in the final sparse table using that. We'll see later in our implementation more details. So it's the matrix, and this is how we merge 2 matrices together. And we merge log matrices together to answer the query. So the total time complexity is this. But we can use divide and conquer too. In divide and conquer, the thing is, for processing each query, we need to only and only pay cost OK per query. So this K3 per query doesn't appear here. Note that first method, this sparse table method, can't solve the full subtask of the problem because Q is so large, and when you multiply Q to log and then K cube, it will get time limit X. But using divide and conquer or disjoint sparse table, you can solve the problem. We'll implement it later. So here what we do is, in divide and conquer, we split the array into 2 parts. We go for somehow prefix sum, but it's different. For the suffix, the right part, and then we go for the same but in suffix for the left part. And for each query, we just need to merge them somehow, but this merge actually operates in OK instead of OKQ. We'll see later in the implementation. So this can be done using divide and conquer, and also we can save all of the values, all of the matrices, and answer queries online using disjoint sparse table. So let's dive into the implementation. Let's implement. So we start with reading N and K, and then reading the array. Like this, and then we read the queries. So let me find a struct for it. And finally I read queries. And like this, and as always I converted to zero based, open, close, open, and we start calling function solve. Finally it prints the answers.
we can do like this. And that's it. So let's start implementing function solve, which is the divide and conquer function. So a note here that we can, as I said, we can directly assign queries to the node they belong just right here, but I'll skip this part and do it with normal divide and conquer to help you understand it more easily. So here we start with getting the mid, and then if a query, so if L plus 1 is R, so this is just a single element, and all queries here, so all queries here, their answer is just 1. For all queries, these queries, it will be 1, and we return. Why? Because it's just a single element, and the number of non-decreasing subsequences of a single element, or it can be 2. Let me see samples. So yeah, empty can be answer, so it's 2. So we start from, so what you are going to do is going from L to mid, and then we have 2 rings. So one is this, and another one is mid to R. So another thing we need to define here is a strict, let's say, base. So the number of base we can do something. And then also, as it works with modes, let me define struct mode int, but it needs to be something that works efficiently. So let me copy my mode ints first, but we need to modify, I think. So for a start, let's have this. Okay. This mode int struct just make us free, and we can easily do every plus operation, anything, and it will handle the rest. So mode int is so base is basically a matrix like this. K times K, and at the beginning they are all 0 for sure, and so we want to insert an element, and there is a boolean. I'll tell you how it works. Its name is inverse. So consider the case. We process some array, and we have base, and it's like Wij. Definition is number of subsequences starting with I, non-decreasing subsequences starting with I, ending with J. So consider all of these subsequences. So we want to add x. When we add x, we want to add x to the end of this array. Note that there is another answer, another non-decreasing subsequence, which is empty, and we need to add 1 finally. But for now, we want to add some x to the end and see what changes in the matrix. So we'll start like this. For each I from 0 to k, so yeah, from 0 to k, we do this. So w of I and x should be, so let's remove this one out. We add all of such things like the sum of all w's from here to here is 0, and we add 1. So consider all of different subsequences starting with I and ending at some j. We want to add x, and now it's like starting with I and ending with x, and we are exactly summing up those numbers. And I use accumulate function, and what it do is just summing up numbers in this range. So that's for insert. But we need another insert too. So we need to have two different matrices actually. So one is for non-decreasing subsequence and one is for non-increasing subsequence. And finally we need to merge this. So it's for our divide and conquer. So when we divide at mid, for this element, for these all of elements, we calculate number of non-decreasing subsequences. And for these elements, they are in the left. So for them, we calculate number of non-increasing subsequences. And finally, we merge these two. So this insert works for the elements to the right, but we need to calculate for them the left too. So for this left, let's define another function. It starts from x, goes to k, and it starts from x, goes to k, and that's it. So okay, for this now let's start here and define base, or it's easier to do it here. Base max n. This. Okay. So base or mid will reset it, and then base for mid and mid starting this element is small. We need to do like this, and let's iterate over the elements to the right. I is mid plus 1, r and plus I, and what we do is first we set base I equal to base I minus 1, and finally we insert increasing the AI, and we do the vice versa. So base of mid minus 1 will be base, and for mid minus 1 it will be like this. Actually, we could insert it, but it's faster, so I did like this. And finally, I see some problem here. So if everything is empty, it's still what we are gonna do. Oh, so this is incorrect. Instead, this is correct. Okay, this is fixed. Then we start from mid -2, and we go for all these elements, and we do this, and again this. That's it. So we calculated base for right and left, and now it's time to answer queries. Let's see if we can answer them. So okay, first we need to define vector of queries like QL, QR. Then if Q.R is at most mid, this query belongs to the left part, like this. Otherwise, if QL starts from mid, this is for QR, but finally, in this case, we need to solve it. So let's solve this. So before we do that, so what we have is we have some calculated thing for left of this query and some for right, and we need to merge them. So for merging, it's like you start at some I, then go to some J, and some K to T, and all these values are non-decreasing. So if we do this, it's gonna be K to the power of 4, which is a lot. So we need to optimize it. So for optimizing it, what we do is fixing just I, which is the first element we are gonna pick from right. And it doesn't matter what we finish with. So if we are gonna finish with I plus 1, I plus 2, it doesn't matter. It's just important that we start with I, and we can have this value for left to make sure they are all less than I. So that's what we are gonna do. So so now I'm gonna iterate over all of the elements to the right, and then I pick some J, which is at the beginning K. Then I iterate first BK minus 1, and then one by one. Oh, interesting. They start from 0, so we can do this, and here we can do this, and removing this, and here we can deduct 1 from every element. So we start by this one, and then here we'll fix the partial sum for this matrix. So here I want to calculate for each element, and for each J, how many ways are there that we start at the beginning is J and finish, it doesn't matter. So it's gonna be just sum of all elements in this array of J in the i's index of ways. So I'm gonna define another array. partial base. So partial base of I, then j will be accumulate of base of I, then w j to the end of it. This works for right, but for left it would be a bit different. No, it will not be different. Exactly the same. So we can define it like this because they are in the vice versa order. So for right, we start from I and we go increasing to j, and for them it's like we start at I and we go decreasing to j. So partial base, let me define it like here. Partial base ij is how many subsequences are there starting from mid, let's say midline, going to I, and is starting with j. So I can be something before me or after me, and it's like, so we have, let's say I, j, then me, and then kl, and what happens here is we need to have partial base of I and also partial base of l. Now for answering each query, consider that we have some elements selected from left, and finally x, and then this is the middle, and then we have y, and then some elements selected. So we want to iterate on x and y. What a note here is x and y can be absent, and they can be absent both. I mean, it's possible that left and right are both empty. So let's iterate on x first, but I start from -1. You will see why. Then on y, and y starts from x because we need this subsequence to be non-decreasing, and it finally leads to k. I will explain why. X equals to -1 and y equals to k means that that part is empty. For example, if x is -1, it means that the left part is empty. And finally, here is the easy part. So answer for this query, we'll add to it. Let me see how I define this. This should be mod into. Okay. So we add to this number of ways we can select something from left, multiplied by number of ways we can select something from right. So let's see. If x is -1, there is only one way. Otherwise, it's partial ways of ql and then x. So it ends at x multiplied by if y is k, it's 1. Otherwise, it's qr -1 and then 1. Seems that we are done here. Actually, we can improve these for loops, but let's see if we can get accepted this current method, and if it was unsuccessful, we'll implement another partial sum here. That's it. So let's solve for QL and L to meet, and then solve for QR, meet R, and finally we print the answer, and that's it. So let's see what happens. I'm gonna use a sample test case to see the result. Okay, so I think we need to replace this with an empty mode end, and again here. Okay, we have some warnings from sanitizer. Oh, the reason is here. Okay, still we have something here. So let's do something for this. Maybe we can use this. Okay, 3, 4, 20. I'm surprised, but it's correct. Let's submit. Okay, I submitted. Let's see. Okay. Let's log in again. Let's submit again. Let's make sure. Oh, we should read and write from and to file. So for that, just before it opens. Let's search this. Okay. Actually, I forgot. And this, last time I participated in a USACO contest was something like 5 or maybe 7 years ago. So let's submit again. Okay, submitted. Okay, it's getting wrong answer on 4 time indexes on almost every test case. So first, let's start with checking mode. Mode is okay. Then max n, just for sure okay for this, at least. Then K, which is okay too. So let's see. Okay, let's try with some example like this, and then one query, 1 to 5, 32, which is correct. Let's try this one, 2. It's okay too. Let's try this one. Let's try something like this. This is good. It's still good. Oh, okay. So let's start doing something like this. Oops. This is also true. Oh. Well, seems correct too. So let's try some test case that will lead to some overflow, maybe 5, 10, 15, 20, and now 30, 30, and 1, and 1 to 30. Seems okay. Let's call it. This seems good too. Where can he debug? Okay, let's try more test cases like this one. One query, then from 3 to 6, 5 is the correct. Well, this says 12, 1 plus 4 plus so 5, then 6, then 7, then 8, then 9, 10, 11, 12. Well, I think this has more than what I counted. See? Our sequence is 1, 3, 2, 4. We have one empty, 4 with single element, then 1, 3, 1, 2, 1, 4, then 3, 4, and 2, 4, and then 1, 3, 4, 1, 2, 4. No, it's correct. Still correct. So we have no choice other than implementing something that verifies we are printing correct answer. That is writing a tester here. So what I'm gonna do is doing some bit math and then counting and then make sure that answer matches. So I will iterate on all masks, and mask length can raise to QR minus QL, and then iterate on every mask, and then we check if this sequence is non-decreasing. So for every I from QL to QR, if mask has the ith bit, then this must be greater than the last element we see, and this is gonna be the new last element. And finally we add naive ans if this was okay, and finally we assert that naive ans matches the answer we found. Okay, let's run and see. This is okay for this test case, but like still okay. So I'm gonna use a random generator here. Then let's generate some random numbers like this, I think, for Vibina. And then I'll generate some integers, and then let's generate some queries. But no, let's just print very simple test case which covers everything, and we run it like this, and it prints some test case for us, and we can redirect input from this to our code, and we have answer. Then we'll generate a lot of test cases like this one, and check if there is some error. Wait, in a lot of these cases we have some runtime error. Well, yeah, even this happens on this case, but okay, this is good. Let's continue. Okay, we have a lot of test cases, and this is going good and printing correct answers for a lot of test cases, which is which makes me more and more confused. So let's try something else here to produce a query like this and print it out. Okay, we need to build this again. Let's check it out again. Is the printing correct answer? So far, good. Maybe we can increase K2. Sorry, there was a mistake here. Okay. Still seems good. It's answering queries correctly. Let's read the problem again to make sure you're doing what problem said. So let's increase number of queries. And again. Let's check if answer is actually working. Yes, this is working too. So the code seems really correct, but we are receiving wrong answer. Oh, this can be because of max Q. I'm not sure, but let's try. Which is 2e5 plus. And this is good, but this is not. Let's check the max Q. Okay, let's stop it again. I don't think it will fix. Okay. Now there is no wrong answer, but there are some runtime or memory limit exit. So let's try some very big test case. Oh, I forget to remove this. Let's try again. Oops, it's getting cases, but tiny limit exit here. So everything was because of this. So the only issue was here. Then let's fix these time limits. So what we need to do is making some partial sum, like then okay, I will move this to here. Then we start from 0. No, we start from 1. We go to k, and partial base of I is going to be partial base of I minus 1 plus partial base of QL and I, and partial base 0 is gonna be 1 plus partial base of QL 0. Then we don't need x at all, we only need y, and we start from 0 here, and here we use partial base of y multiplied by this. So let's make sure it's printing correct answer. For sample test case 1 to 16, it's not correct. Let's see what happened here. 0 is oh, this is the issue. So we need to go to k actually. Okay, this is fixed. Let's submit again. Still, we have a lot of time limit exits. To do something better here, we need some optimizations. First, let's start this input optimization to see if it's gonna work. It didn't work. Then let's do this, and also let's optimize this one. Good. This will speed up our code a bit. Let's try it. Let's try it. Submit again. Okay, great. We successfully solved the problem and got AC. The final trick I used was to, instead of every time getting mode, I used these handmade functions for plus, and it made our code much faster, and we got accepted.
Thanks for watching. If you found this video useful, please like, subscribe, and ring that bell. By the way, YouTube thinks the video down here is just perfect for you. Give it a watch and let me know in the comments.